Welcome to this lecture number 12 of the course Computational Hydraulics. We are in module 2 numerical methods, and in today's lecture we will be covering unit 8 partial differential equation numerical stability of one dimensional PDE. What is the learning objective for this particular unit? At the end of this unit, students will be able to analyze the numerical stability of discretized one dimensional conservation law in terms of partial differential equation. Let us consider our general equation with a general variable phi. We have seen that initially with this first term in the right hand side, we have solved boundary value problem with our temporal term and boundary value problem or right hand term, this one and this one, we have solved initial value boundary value problem, and in these boundary value problem or initially boundary value problems, we have considered S phi or sourcing term. Now we need to consider the second term in the left hand side. This is somewhat related to a velocity term, and we should analyze this term before starting our finite volume approach. So, in this case, one dimensional conservation law in terms of phi can be written as del phi by del t and del f phi del x S phi. S phi is sourcing term, this is temporal term, and this is spatial term only in one dimension, that is x. So, what is this f phi? F phi is the flux function, amount of phi that passes at the axis of x per unit time due to displacement of phi, and f phi does not depend on derivative with respect to derivative of phi with respect to space or time, and S phi is sourcing term. This is the amount of phi that appears per unit volume irrespective of the amount transported via flux. So, with this information we can proceed. We can see that we have phi which is a function of x and t only. So, one dimensional in space and we have one time dimension. So, for example, in this case phi can be u phi. If phi is equal to u phi and lambda phi equals to 1 and our epsilon phi equals to 1, then we can get this equation without the right hand first term and other fourth term on the right hand side. However, any derivative in this f phi is not allowed. So, this is related to diffusion. So, this gamma x is like diffusion coefficient. So, this is not allowed for this kind of equation, because we have derivative of phi with respect to space or in one dimensional case. So, we can write the non-conservative form where del phi by del t, and this is actually lambda into del phi by del x. This is written in terms of our general variable phi, not in terms of flux f phi. So, what is this lambda? Lambda is equal to del f by del phi, and we have this modified sourcing term. This is S phi minus del phi, this is constant. So, actually we can write our f phi del by del x as del phi, this phi into del phi by del x plus del f phi by del x, where phi is constant value. So, now this term is lambda, and we can change this side for this term, and if we subtract transfer this term on the right hand side and subtract from original sourcing term, then we can get this modified one. So, let us utilize our explicit upwind scheme. What is this upwind? Depending on this value of lambda or sign of lambda, we generally change the scheme. If it is positive or negative, we need to change our discretizations in space. So, we have our original conservative form equation, we are discretizing it at the I n level, this is present time level. So, if we consider in this case we have one space axis and one time axis available for this one. In this case, if we have I minus 1, I plus 1, then for time discretization we have nth level n and n plus 1. For space discretization we have I minus 1, I plus 1. These values are actually unknown values and these are our known values. So, with this information we can discretize our space derivative for flux. So, interestingly, in this case, if lambda I n is positive, that means lambda equals to flux. So, change in flux with respect to variable phi that is positive, then we will be utilizing this derivative I minus 1 for del phi by del x, and if lambda is negative, then we will be utilizing f I plus 1 minus I value for this one. And in this case time discretization is of order delta t and space discretization is of order delta x. So, overall accuracy for this one is delta x delta t. And for sourcing term, this is simple, we will be evaluating at IN level. Now, we can write our final solution like this. If we change the sides for known variables on the right hand side, this is unknown level, this is known level, this flux is also known, these values are known, this is also known. So, we can write like this. Now, we need to analyze the stability of this particular scheme, but von Neumann stability analysis can be performed for linear equations. Let us consider that the flux term can be written in terms of A phi, where F phi equals to A phi and A is some constant value. So, lambda is del f phi by del phi, which is A. Depending on the sign of this A, whether it is positive or negative, we can change the space discretization. Now, let us consider that error equation, again it can be error term epsilon I n can be written in terms of amplitude and this phase thing for x direction. So, we have this I n and A n I var phi x corresponding to that direction. Now, with this information we can proceed for stability analysis. Now, we can bring that A term out of this bracket and we can write like this for A greater than 0 and less than 0. Now, discretized governing equation for this initial boundary value problem, but in this case boundary initial condition is the main thing, because one side only it is defined. So, it is like initial value problem. Now, this is the solution which is coming from infinite precision computer, and this is the amount of error involved in a particular step and particular discretization level. With this we can also write the discretized finite difference equation for exact solution. This is the exact solution thing, and exact solution should be satisfy our original finite difference discretization. So, we have written phi hat I n plus 1 and others are at known time level. Now, if we subtract our this exact solution equation discretized form from this one, we can get the corresponding error equation. So, error equation can be written like this, where this one is unknown and these are known level things. Now, as per our definition, we can write this epsilon I n plus 1, where only change in the amplitude, no change in this index for I n, this is A n I var phi x, I minus 1 only change in index for I I plus 1 only change in the index for I. So, with this expression, if we write our growth factor by dividing epsilon on both sides, this is epsilon I n plus 1 divided by epsilon I n, and interestingly this is equal to a n plus 1 divided by a n. Now, for a positive we have this form, a negative we have the second equation. Now, if we further simplify this one, we can write like this, where this e to the power minus part is there. So, minus I minus this imaginary number into var phi x, and this is 1 plus 1 minus e to the power imaginary number y phi x again for negative value. Now, in this case we can define a number which is CR, and CR is defined like this: modulus of A into delta t divided by delta x. So, always CR is positive. Now, the problem with this one is that in this case, if A is negative, we can write this equation as 1 minus modulus of A into delta t divided by delta x 1 minus e to the power minus 1 into var phi x, only for negative value. Now, with this CR we can proceed and we can define our amplification factor in terms of real and imaginary part of G in simplified form. Now, as per our von Neumann stability criteria, this modulus of G should be less than equals to 1. Now, we need to evaluate the modulus of G. So, if we evaluate the modulus of G in this case, so basically we are taking square of the real and imaginary part. Now, this comes to this simplified form: 1 plus 4 CR minus 1 sin square phi x by 2. In this case, important point is that this quantity is always positive. Now, as per our condition, G mod square should be less than equal to 1. If CR equals to 0, then we have 1. If CR equals to 1, again this is equals to 1, and for values less than 1 and greater than 0 for CR, we can get G modulus square less than equal to 1. So, we can see that for this condition where CR is greater than 0, less than equal to 1, this scheme is stable. This is known as Courant-Friedrich-Lewy condition or CFL condition. Thus, we can say that explicit scheme is conditionally stable, and this is the actual condition. Now, from geometrical point of view, if we see, we can represent our G, where G is equal to 1 minus CR plus CR cos var phi x plus square root minus 1 and within bracket minus CR sin var phi x, this quantity. So, this part is represented in the real axis or REG, and this part is represented in the imaginary axis. So, this part is 1 minus CR and this one is the projected one. So, this length is CR into cos phi. So, total length, this part is actually our real of G. Now, and in this case, this part is imaginary component of G. So, this thing, this modulus of G should be within this circle with unit radius for stability. So, we can say that in this case, if CR value is within 0 to 1, this condition will be satisfied. That means, this circle will be within this bigger circle. So, our stability criterion will be satisfied. Now, if we consider implicit upwind equation, we are discretizing it at n plus 1 level. Now, if we consider our time discretization, this is our time discretization. We have truncation error of order del t. For space discretization, again values are at n plus 1 levels. For lambda I n plus 1 greater than 0, lambda I n plus 1 less than equal to 0. This is again of order delta x. So, overall accuracy of the scheme is delta x delta t. This is for source term, and this source term is discretized at n plus 1 level. Now, with this we can get the final solution, which is in terms of values at nth level and flux terms at n plus 1 level, sourcing terms at n plus 1 level. This is for this should be evaluated at n plus 1 level, not at the nth level. So, stability analysis, again if we consider this, we need to see our final solution, we can again discretize the governing equation with a implicit scheme, and in this case we can write the exact discrete equation for the finite difference solution. So, in this case we are getting the equation in terms of errors for epsilon I n plus 1 and epsilon I minus 1 n plus 1, all these are at n plus 1 levels, only the first term is at nth level. So, we can write our amplification factor by dividing it with epsilon I. Again defining the Courant number like this, where this is always positive. So, we can write G like this. If we further simplify, we can write G in this format. Now, we need to define the modulus for this G to evaluate the stability of the scheme. In this case, considering the thing for a greater than 0, we can write like this, and with this we need to evaluate the G square. This is the conjugate complex number in this case. So, with this, if we proceed and write this thing for G square, G modulus of G square, we can get this one, and further simplification will give this G square condition. In this case, we can see that CR is always positive. A sine square of phi x by 2 is always positive. So, CR plus 1 is positive, CR is positive. So, 1 by 1 plus something positive, this will give always this G square or modulus of G squared less than equal to 1. For extreme condition, this will be less than equals to 1. So, we can see that for implicit scheme it is unconditionally stable. Now, we have covered the finite difference thing. In the next lecture onwards, we will be starting finite volume. Thank you.